Picture this for a second. Our galaxy, the Milky Way, holds somewhere between 100 to 400 billion stars. Now let's keep it simple and say each of those stars has just one planet. That's potentially 400 billion planets in our galaxy alone. But hold on, it gets wilder. The entire universe. Scientists estimate it's home to around 2 trillion galaxies. That's galaxies, not stars. So when you zoom out and do the math, the number of stars out there is practically unthinkable. In fact, some researchers say there are more stars in the universe than grains of sand on every beach on Earth. Let that sink in. If even a fraction of those stars had planets like ours, the universe should be teeming with worlds, some maybe even with life. Intelligent life. Civilizations. Maybe even ones way more advanced than we are. So, where are they? With all that cosmic real estate, you'd think someone out there would have reached out by now, sent a signal, left a trace, something. But we've heard nothing. Not a whisper. No signs. No messages. This mystery has a name. The Fermi Paradox. And at its heart is one hauntingly simple question. If the universe is so full of possibilities, why does it feel so quiet? Where is everyone? What if the answer to one of the biggest mysteries in science has been hiding in plain sight, right in our cosmic backyard? Recently, astronomers may have stumbled on a major clue that could help explain why the universe seems so eerily quiet. It turns out, we might be living in the middle of a massive empty zone in space. It's called the KBC void, also known as the local hole, and it's unlike anything we've seen before. This thing spans about 2 billion light-years across. That's not a typo. 2 billion. To put that in perspective, it's one of the largest known voids in the universe, and it's where we happen to be, right near the center. This discovery is shaking up some of the most basic ideas we've had about how the universe works. It's raising huge questions about the Big Bang, how galaxies are spread out, and even how fast the universe is expanding. But the real twist? This bizarre empty zone might actually help solve not just one, but 2 of astronomy's biggest unsolved mysteries: the Hubble tension and the Fermi paradox. Now you're probably wondering, how did we even figure this out? How do we know we're sitting inside a cosmic bubble that's nearly empty? That breakthrough came thanks to 3 researchers: Ryan Keenan, Amy Barger, and Lennox Cowie. They used something called galaxy redshift surveys, which is just a fancy way of saying they measured how light stretches as galaxies move away from us. That data let them build a 3D map of the universe, and that's when things got weird. Their map showed a huge spherical area, about 2 billion light-years wide, with far fewer galaxies than expected. This region isn't just empty. It's 7 times larger than your average cosmic void, and we're right in it. So, what does all this mean? Could this giant void explain why we haven't picked up a single message from another intelligent civilization? Could it be the missing piece of the puzzle that finally helps us understand why the universe seems to be expanding faster than expected? Big questions, fascinating clues, and maybe, just maybe, we're closer than ever to some real answers. At first, when scientists started talking about this gigantic cosmic void, the KBC void, most people in the field were skeptical. And honestly, who could blame them? The idea of such a massive empty region in space didn't just sound strange, it directly challenged some of the core beliefs about how our universe is supposed to work. Here's why it was such a big deal. Problem number 1, something called the cosmological principle. It's basically the idea that on a large enough scale, matter in the universe is evenly spread out. Galaxies here, galaxies there, no huge clumps or empty patches. But the KBC void, it's not just a small pocket. It's a giant stretch of space with way fewer galaxies than there should be. That throws a wrench into one of the main assumptions behind our entire model of the universe. Problem number 2, simulations. Scientists use supercomputer models, like the massive MXXL simulation, to predict how the universe should look based on our current best theory, the lambda CDM model. And according to those models, a void this big shouldn't exist. The gravitational forces just aren't strong enough in those simulations to carve out something this vast and underpopulated. But then, the data kept coming in. More galaxy surveys, more telescope scans, more evidence, and little by little, the picture became crystal clear. This void is real. It spans roughly 2 billion light-years across, and there's just no getting around it. And here's the wild twist. What started out as a problem for our standard model of the universe might actually be the clue we've been waiting for. That mysterious empty space could help explain one of the biggest puzzles in modern astronomy. The Hubble tension, a strange mismatch in how fast we think the universe is expanding. Scientists have been scratching their heads over this for more than 60 years. But maybe the answer has been right in front of us, well, around us, the whole time. Funny how the universe works, right? Just like getting lost in too many browser tabs, sometimes the thing you're looking for is buried beneath layers of information. And sometimes it's hiding in a quiet, empty corner of space. Here's something wild. The fact that we're living near the center of a massive cosmic void, the KBC void, might actually be the key to solving one of the biggest mysteries in modern cosmology, the Hubble tension. So, what is the Hubble tension? Let's break it down in simple terms. It all starts with one big idea. The universe has been expanding ever since the Big Bang, and the speed at which it's expanding, that's measured by something called the Hubble constant. Basically, it's like a cosmic speed limit. It tells us how fast galaxies are racing away from each other as the universe keeps stretching out. Now here's where the problem begins. Scientists have 2 different ways of measuring this speed, and they keep getting 2 different answers. The first way is direct. Astronomers look at galaxies that are relatively close by and use special cosmic mile markers like pulsating stars called Cepheid variables and bright exploding stars, supernovas, to figure out how far away those galaxies are. Then, they measure how fast those galaxies are moving away from us. That gives them one version of the Hubble constant. The second way is more like time travel. Scientists study the cosmic microwave background, that faint glow left over from the Big Bang itself. This light has been traveling through space for over 13.6 billion years, giving us a snapshot of what the universe looked like way back in the beginning. Using detailed models of how the universe evolved from then until now, they calculate what the expansion rate should be today. Here's the twist. Those 2 methods don't match, not even close. It's like checking your speedometer and GPS and getting 2 totally different numbers. That mismatch is what we call the Hubble tension, and it's been driving scientists crazy for years. But now, thanks to this discovery that we might be living in a huge underpopulated region of space, we may finally have an explanation. If the local part of the universe is less dense than the average, it could make nearby galaxies appear to be moving faster than they actually are, messing with our direct measurements and creating this apparent tension. So, could this giant cosmic void we're in actually be throwing off our entire perspective on how fast the universe is growing? It's a mind-blowing possibility, and maybe, just maybe, the beginning of a long-awaited answer. And here's where things start to get tense. Literally. When scientists measure how fast the universe is expanding, they get two different answers depending on how they measure it. When they look at nearby galaxies, they calculate the Hubble constant to be about 73 kilometers per second per megaparsec. But when they look way back into the early universe, using the glow from the Big Bang, they get a slower rate, around 67 kilometers per second per megaparsec. At first glance, that might not sound like a huge difference, but in science, especially at this level of precision, that gap is a big deal. It's not just a little wiggle room or a margin of error, it's a statistically significant mismatch. And that means something might be off in how we understand the universe. But it doesn't stop there. This disagreement also messes with how we estimate the age of the universe. Here's how that works. If you know how fast the universe is expanding today, your Hubble constant, you can sort of hit rewind and figure out how long it's been expanding since the Big Bang. That gives us an estimate of the universe's age. Now here's the kicker. Using the higher Hubble value from nearby galaxies suggests the universe is about 12.5 billion years old. But the slower value from the early universe says it's more like 13.8 billion years. That's more than a 10% difference in the age of everything. Stars, galaxies, us. That's not just a rounding error. That's a cosmic contradiction. And that's why the Hubble tension is such a big deal. It's not just about numbers on a chart. It might be a sign that there's something missing from our picture of the universe. Maybe something's off with our understanding of dark energy or dark matter, or maybe even gravity itself. Whatever the answer is, it could lead to a major breakthrough, something that rewrites the rules of modern physics. But what if the Hubble tension, the mysterious mismatch in how fast the universe is expanding, has a surprisingly simple explanation? It might all come down to where we are in the universe. See, we live inside something called the KBC void, a massive cosmic bubble that's strangely underpopulated. Compared to other regions of space, this area has fewer galaxies and less matter overall, and that changes everything. Because here's the thing, less matter means less gravity pulling things inward. Meanwhile, the denser regions outside the void have more mass and more gravitational pull. So objects in our local area are slowly being tugged outward by those heavier regions on the edge of the void. And that sets up a kind of cosmic optical illusion. From our perspective, it looks like everything around us is expanding faster than it actually is, simply because we're inside this low-gravity pocket being stretched outward by the rest of the universe. When scientists measured the matter density inside the KBC void out to a distance of about 300 megaparsecs, they found it's roughly 20% lower than the universe's average density. And guess what? That lines up with earlier findings showing that our local expansion rate appears to be about 11% higher than the global rate. In other words, this giant void might be tricking us, creating the illusion of a faster expansion and possibly solving the Hubble tension. But this also opens up another can of worms. The very existence of the KBC void puts pressure on our most trusted cosmological model, the Lambda Cold Dark Matter model, or Lambda CDM for short. This model has been the gold standard for explaining the structure and evolution of the universe. It's based on the idea that matter is spread out evenly on huge scales and that the universe's current structure formed from tiny fluctuations in the early cosmos. But here's the twist. LCDM doesn't expect a void this big to form. it predicts that space should be relatively smooth at such scales. To test this, scientists ran new simulations. They tweaked the initial density fluctuations and made the universe's structure formation process more efficient. And yeah, that produced a void like KBC. The catch? The new results no longer fit within the lambda CDM model. Instead, researchers had to turn to a different theory, modified Newtonian dynamics, or MOND. MOND is a bold idea. Rather than assuming the universe is full of invisible stuff like dark matter, MOND suggests that maybe gravity itself works differently on large scales. It was originally proposed to explain why galaxies rotate the way they do, without needing to add unseen mass. Now, MOND and lambda CDM differ in two major ways. And if you're curious about those differences, or what MOND might mean for the future of cosmology, stick around, because that story is just getting started. So, what exactly is MOND, and how does it shake things up? First off, MOND, short for Modified Newtonian Dynamics, takes a pretty bold approach. Instead of relying on the idea of invisible dark matter to explain how galaxies behave, MOND says, what if gravity itself just works differently at really low accelerations? That's the first big change. Second, MOND also predicts that galaxies and galaxy clusters form faster than they would in the standard lambda CDM model. That quicker growth makes the formation of large, empty regions, like the KBC void, more likely in a MOND-style universe. Now here's the tricky part. Some observations out in the cosmos line up better with MOND. Others still support lambda CDM. So right now, we're stuck in this ongoing tug-of-war between the two theories. Neither one has completely won the argument, and we're still left with one big unsolved mystery. What is the universe really made of, and how does it work? The discovery of the KBC void might be the clue that forces us to rethink everything. It suggests that some long-standing ideas in cosmology might need to be tweaked or tossed out entirely as new evidence comes in. Because if the universe isn't as uniform as we thought, if there are major local differences in matter and density, that could mean we need to go back and reevaluate some pretty fundamental concepts. Things like how cosmic structures form, or even how dark energy works, might not be as set in stone as we believed. And here's where it gets even more interesting. Living inside this giant void might also help us understand one of the most unsettling questions in all of science, the Fermi paradox. If the universe is so vast and full of potential for life, then where is everybody? Why haven't we heard from any other intelligent civilizations? Well, being tucked away in an underpopulated, low-density part of the cosmos might actually be part of the answer. There are three big ideas to consider here. Ready to dive into them? Let's break it down next. First up, isolation. The KBC void is like the rural countryside of the universe. Huge, quiet, and mostly empty. It has way fewer galaxies than the more crowded regions, which also means fewer stars and fewer chances for planets that could support life. So, if intelligent civilizations are more likely to pop up in those busy, star-filled areas, that puts us way out in the sticks. We might simply be too far away from anyone else to notice them, or for them to notice us. The second, distance and scale. Even if there are civilizations somewhere near us on a galactic scale, we're still talking about mind-blowingly huge distances. The galaxies inside the KBC void are incredibly spread out, so any signals, even traveling at the speed of light, could take millions of years to reach us. That means even if someone is trying to communicate, we might not get the message for eons. It's not that no one's out there. It's that the cosmic scale makes a real-time conversation almost impossible. Third, avoidance, or just plain indifference. Let's say advanced civilizations are out there, and they've figured out how to find other life forms. What if they're intentionally avoiding us? They might have a rule not to interfere with younger, less advanced civilizations, like a cosmic version of Star Trek's Prime Directive. Or maybe we're just too off the grid to show up on their radar. In a universe with trillions of galaxies, they might focus on dense, high-energy zones full of activity and resources, not the quiet outskirts like our void. So even if they exist, they might not see us as interesting enough to visit or reach out to. All of this gives us a pretty compelling answer to the Fermi paradox, that strange silence from the stars. Maybe it's not that we're alone. Maybe it's just that we're in the middle of nowhere. And here's a deeper twist, the anthropic principle. This idea says the universe appears the way it does because we're here to observe it. So maybe the only reason we're even asking these questions is because we had to be in a place like the KBC void for life like ours to evolve in the first place. Maybe this quiet, isolated corner of the cosmos gave us just the right conditions to exist and wonder about the universe. Now, here's where things get really mind-bending. When we talk about the KBC void and where we are in the universe, there's this idea floating around called the anthropic principle. Sounds fancy, but here's the gist. It suggests that we're not in this low-density, quiet corner of the cosmos by accident. Our spot in the universe, surrounded by less matter, fewer galaxies, and a lot of cosmic silence, might actually be exactly what was needed for life like ours to develop in the first place. If the universe were evenly packed with matter everywhere, no massive voids, no empty stretches, then the delicate balance that made Earth, stars, and complex life possible might have never happened. So, the KBC void might not be a strange outlier after all. It could be the kind of place where observers like us naturally show up. Wild, right? But let's keep it real. This idea, the anthropic principle, has its critics. Some scientists love it. Others roll their eyes, calling it more philosophy than science, because it doesn't offer a clear way to test or prove it. Still, the discovery of the KBC void adds a fascinating new piece to the cosmic puzzle. Whether it's explaining why the universe expands the way it does, looking at you, Hubble tension, or why we haven't met any alien pen pals yet, this giant, empty patch of space just might hold answers we didn't even know we were missing. So, will the KBC void end up being the key to one of the biggest mysteries in cosmology? We're still figuring that out, but you better believe all eyes are on it. Thanks for watching, and stay curious out there.